The objective of this experiment was to apply the knowledge acquired throughout the course to develop and test a robot program for a specific application. All of this going through a process that involved trajectory selection, target definition, programming, simulation, robot calibration, and testing with robot ABB. As part of the project specifications, we had to choose a design proposal that would meet a trajectory of a minimum of 50 points and 8 distinguishable arcs. The drawing was to be portrayed on a visible XY plane and previously approved by the designated teacher. Aspects such as complexity and originality were to be evaluated and considered. According to our first trajectory selection, we browsed a series of 2D models and proposed 2 designs that contained the minimum number of points and arcs required. After receiving approval from our teacher, we proceeded to select a proposal that would accurately fit our project visualization and expectations. We contemplated the general design of the proposal and plotted the most prevalent points that created the design's layout with red dots. In the same way, we drew out yellow arcs to point out the selected use of arcs in our design. Finally, we ended up with a total of 99 estimated total points and 9 estimated arcs, therefore meeting the project's initial requirements.
We then proceeded to establish our general location to specify the working area, where we will be plotting our proposal. This was done with a general interval of 350 units to 650 units in the x-axis and minus 200 units to 200 units in the y-axis. Due to the complexity of our design, we sectioned out the point that made up the design so we could establish a more concrete trajectory for the robot, enabling a more optimized drawing sequence and time reduction. We ended up with a total of 9 sections that will make up our model and 3 approximation points to give the robot a better sense of access to coordinates. We then distinguished each face with a different color and proceeded to adapt the coordinates that belong to each point. With the help of a square grid laid on top of the design, we assigned coordinates for each movement and made sure they made symmetrical sense as part of the drawing. After covering every face, we went over the trajectory and identified each point as a possible move L, move J, or move C movement that will later be transcribed to the programming aspect of the project. After labeling every point with its significant coordinate, we proceeded to bring the model to life through the Robot Studio software application. We made sure to create a solution that will include an IRB 146 kilograms 0.81 type of robot with a MT02 symmetric tool as previously specified in the instructions. As to the programming process, we start out by transcribing all coordinates in the work object and point section, according to the pre-established points from the proposal. Secondly, we then retranscribe the coordinates on the trajectory and procedure section, where the order of coordinates automatically establish the simulation's trajectory according to the pre-established points. Since the system labels each coordinate as a movable kind of movement, we proceeded to manually change any point that had to be specified as move J or move C according to the proposal's design. After all movements were assigned accordingly, we specified the tolerances, so they were altered to fit the movements adequate to our design. Finally, we repeatedly simulated our program until our design requirements were met and the desired simulated shape was acquired. We can observe the final simulation design as follows. Despite acquiring a successful design, there were several problems we faced while generating our model in the software application, such as trouble engaging the tool and the robot with specified compensations, for which we had to create new specifications for the tool on a separated section that will enable the compensation in order to fix it. Secondly, at the beginning of the programming process, tolerances were not corrected and therefore errors will prevail throughout the program. In this case, we had to go over the whole program, correcting every tolerance and any kind of incorrect movement or location of points, until the robot showed the perfect reach to each section and the program appeared symmetrically accurate. We also had to deal with the incorrect location of points and random ampere positioning. Nevertheless, once the simulations were running, we could visually locate any kind of point that was not symmetrically to its opposing pair or didn't make sense as part of the original design. After locating inaccurate points, we will proceed to change them and fix this problem. Lastly, the software will frequently crash or freeze after a number of simulations, to which we had to restart the program every time the site froze, in order to get rid of build-up content and enable it to start running once again.
As part of our final conclusions, we realized how useful robots really are as utilities, and that they can be adapted to any kind of labor environment for any kind of recreational or practical purposes. In the same way, we realized that once the concept of programming has been adequately adapted, it is possible to achieve a variety of automated functions that can serve customized purposes. Robot Studio is a very amicable and functional software that can serve several industrial purposes due to its extensive set of advantages. Therefore, it is important to take advantage of the given platforms and implemented softwares, such as this one, to develop our technical and programming abilities that can later be applied in our potential field of work.